Welcome back. In our last videos, we have discussed on how to convert between the forms of a complex number, from algebraic form to exponential form, as well as to the polar form. We have also discussed in detail as regards to how you can find the modulus of a complex number and the argument of a complex number. Those two are very, very important when trying to write the polar form as well as the exponential form. Now, in this video, we'll be taking it a step further and discussing the Moivre's theorem, which guides how we express the power of a complex number in terms of multiplying it multiple times, as well as taking the root of a complex number. So we take it step by step. Do not forget, for a general complex number, z is equal to a plus ib, we have the modulus to be equal to the square root of a squared plus b squared, and then we have the argument to be equal to the tan inverse of b over a. Now, taking those concepts, the Moivre told us that when we have this complex number and we multiply this complex number by itself multiple times, right, there is also a corresponding effect this has on the modulus and the argument of that multiplied complex number. In fact, it tells us that if the basic complex number normally is indeed r cos theta plus I sin theta, then when we continually multiply it by itself, the power of that complex number can now be represented as r raised to the power of n into cos n theta plus I sin n theta, where of course in this case we have that n is equal to 0, 1, 2, 3, and so on, right? So as far as we have a complex number in this form, then the power of that complex number can be expressed, that's a multiple of that complex number by itself, can be expressed in this identity, right? Z raised to the power of n is equal to r raised to the power of n into cos n theta plus I sin n theta, where n can be 0, 1, 2, 3, and so on and so forth. Now, you might wonder that why exactly are we picking n to be 0, 1, 2, 3, and so forth? The reason why we can do this is because we have that when n is 0, you have z raised to the power 0, which will be equal to r raised to the power of 0 into cos 0 plus I sin 0. Sin 0 is 0, cos 0 is 1. And r raised to the power 0 will of course be 1 because r, which is the modulus, would not be 0 unless the complex number itself is 0, right? So that is the only instance where you take z to be 0, right? So we can say that this holds provided z is not 0, right? Because when z is 0, you would not be able to take the power of n, or you could not be able to take the value of n when it is 0, right? So this holds true. Of course, when you take z to be 0, it just means n will start from 1. So instead of this, you can also say or n is equal to 1, 2, 3, and so on, with z equal to 0 inclusive. So dependent on how you decide to translate it, this would still work flawlessly. Now, as far as the concept of the Moivre's theorems are concerned, it doesn't just stop in terms of multiplying a complex number by itself. It also talks about what happens when we multiply a complex number by another complex number. Recall that in one of our videos, we have discussed what happens when we multiply two complex numbers together in terms of their algebraic form. But when we discuss the multiplication in terms of the polar form, what exactly would it look like? This time around, we'll see that if we have z1 to be equal to r1 cos theta 1 plus I sine theta 1, and then of course we have z2 to be equal to r2 cos theta 2 plus I sine theta 2. We will then have that z1 multiplied by z2 would be the same thing as their modulus multiplying themselves into cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. This tells us the multiplication of complex numbers. Similarly, we can also talk about the division of complex numbers, which says we will simply divide the respective modulus and then cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Of course, in this case, the order of arrangement is very, very paramount. When you take z1 divided by z2, then the modulus of z2 comes as denominator, and then the argument of z2 is the one that is being subtracted. So these are very, very important notices as far as the Moivre's theorem is concerned. Now that we have these representations, of course, we can go ahead to take some simple examples to see exactly how this can be used.